Welcome, everyone, to the Deep Dive. If you are tuning in right now, there is a very good chance you are gearing up for a major strategic meeting.
Or maybe you're an engineering lead.
Right,
Okay.
exactly. An engineering lead trying to figure out how to structure your team for the next 5 years. Or, perhaps you're just trying to stay afloat in the absolute tidal wave that is the modern tech curve.
It really is a tidal wave right now.
It is. It
Yeah.
totally is. And whatever brought you to the Bite-Sized Tech News TLDR podcast today, our goal is incredibly straightforward. We are going to cut right through the industry noise, ignore the superficial hype, and get straight to the bottom line. Okay, let's unpack this.
Let's do it.
Today, we are taking a deep dive into a profoundly disruptive concept. It was outlined in a recent YouTube video from our very own channel, and the title of that video is The Rise of Write-Only Code: Why Humans Won't Read the Future.
A provocative title, for sure.
Super provocative. And I have to be honest, when I first saw that title, my immediate reaction was, it was skepticism. I mean, it sounds a little strange.
Maybe a little dystopian.
Yeah, dystopian. It evokes this image of a dark server room where algorithms are just silently rewriting themselves while the humans are locked outside. But as we dig into the source material, it becomes really clear that this isn't some science fiction thought experiment.
Not at all.
It is a fundamental shift in how we are going to build software, manage technical teams, and establish trust in the systems that literally run our world.
And that initial skepticism, I mean, it's completely natural. Frankly, it is a healthy reaction for any professional who has spent their career operating under the current paradigms of software development. But my role today is to strip away the philosophical fluff.
Right, no fluff.
We need to look purely at the operational reality. We're going to get straight to the hard facts of this impending software revolution. The mission of this deep dive is to clearly explain the real-world implications of write-only code and to rigorously pinpoint the immediate productivity and security impacts for you.
For you, the professional dealing with this on the ground.
Exactly. We are barreling toward a future, and I mean the very near future, where the code that runs critical infrastructure, from complex financial routing to global logistics networks, is generated, tested, and executed without a single human ever laying eyes on the syntax.
Wow.
That is the core premise of our source material today. It is a reality that is arriving far faster than the broader industry is currently prepared to handle.
It really does sound like a massive leap, though. You hear that and you immediately think, wait, we were just going to let the machines take the wheel entirely.
That's the fear.
Because right now, the standard operating procedure for almost every tech company on Earth involves an engineer writing code and then another engineer,
Or a whole team of them.
right, a whole team sitting down with a cup of coffee to meticulously read through those lines of code before anything goes live. To suggest that this entire process is about to just vanish requires some serious justification.
It absolutely does.
So before we get into the mechanics of how write-only code actually works, we need to understand why this shift is happening at all. The source material argues that to understand this, we have to look back at a foundational, recurring pattern in software engineering history.
The cycle of bottlenecks.
Yes, this constant, almost ruthless cycle of bottlenecks. Can you walk us through what that cycle actually looks like in practice?
If we connect this to the bigger picture, this cycle of bottlenecks is essentially the fundamental engine driving all technological progress over the last 50 years. The software industry does not evolve in a smooth, linear fashion.
More jagged.
Very jagged. It evolves through a series of punctuated equilibria driven by constraints. The pattern is always the exact same. The industry identifies a massive, systemic bottleneck that is slowing down the delivery of value. Entire organizational structures, budget allocations, and professional cultures are built around managing that specific bottleneck. Then an innovation arrives that completely destroys that constraint. But the friction doesn't vanish. The moment you widen the pipe in one place, the pressure immediately builds up at the next narrowest point in the system. You slam right into a new bottleneck.
You fix one traffic jam and just create another one down the highway?
Precisely. Understanding this historical context is critical for you, the listener, because it demystifies the current AI boom. This isn't just a random hype cycle driven by venture capital. The transition to write-only code is the inevitable structural breaking point of our current, highly optimized era of software development.
I really appreciate that perspective because it grounds the conversation. We aren't just talking about cool new tools. We are talking about macroeconomic shifts in how work gets done. And the source uses a brilliant historical example to illustrate this cycle.
The infrastructure shift.
Yeah. It references the shift in how we managed infrastructure. Now, most of our listeners are deeply familiar with modern cloud architecture, but the source asks us to look back at the era of physical data centers to really see this bottleneck cycle in action.
Yes. The source uses a classic industry analogy to illustrate this perfectly.
Heh.
The transition from treating infrastructure as pets to treating it as cattle.
I love this analogy.
It's so accurate. Think back to the days of strictly on-premise hardware. A physical server was a highly precious resource. The fundamental bottleneck for any technology business was capital expenditure and physical procurement.
You couldn't just spin something up.
No. If you want to launch a new service, you couldn't just write the code. You had to forecast your capacity needs months in advance, order the physical hardware, wait for it to be shipped, rack it in a data center, wire it for power and networking, and manually install the operating system.
It took forever.
Those servers were treated like pets. They were given names.
Oh, yeah, like Server Zeus or Database Apollo.
Exactly. They were lovingly maintained. If Zeus started overheating, an engineer would get a pager alert at 2 in the morning, and they would manually log in to nurse that specific machine back to health. The constraint on innovation was the physical manipulation of silicon and copper.
And because that was the bottleneck, the entire culture of IT was built around it. You had massive operations teams, rigid deployment schedules, and a deep, deep aversion to change, because changing things meant touching the bets.
And if a pet died, the business went down.
Exactly. But then, as the source points out, that bottleneck was just obliterated. The cloud arrived, Amazon Web Services, Azure, Google Cloud. They completely abstracted the physical layer, and suddenly we weren't dealing with pets anymore.
The paradigm shifted to cattle. In a cloud-native environment, servers are nameless, disposable compute resources. You don't name them Zeus. You assign them a randomly generated hash string.
Just a string of letters and numbers.
Right. If a server acts up today, you don't send an engineer to nurse it back to health. You simply terminate the instance and let an automated scaling group spin up a brand new one in milliseconds via an API call.
Just boom, gone, replaced.
The physical hardware bottleneck was completely destroyed. But true to the historical cycle, the friction didn't disappear. The moment compute became infinitely scalable and instantly available, the bottleneck shifted immediately and violently to a new area: developer velocity.
Right, because suddenly the infrastructure is just sitting there. It's essentially tapping its foot, waiting for you. You can provision 10,000 servers across 3 global regions in a matter of seconds, but those servers are entirely useless without application logic running on them.
They're just empty boxes.
So the question for the entire industry became, how fast can a human being actually turn a business requirement into working code to deploy onto this infinite infrastructure? And for the last, 15 to 20 years, that is where all the money, time, and innovation has gone. We have obsessed over developer velocity.
We truly have. If you look at the dominant trends of the last 2 decades, they are all entirely focused on optimizing the human developer's output. We invented agile methodologies to streamline project management.
Sprints and scrums.
We built continuous integration and continuous deployment CI/CD pipelines to automate the testing and release processes. We developed incredibly sophisticated integrated development environments, IDEs, that catch syntax errors in real time.
Everything to make typing faster.
We moved to microservices architecture so teams could work independently without stepping on each other's toes. Every single one of these innovations was designed to make the human typing on the keyboard faster, more efficient, and less prone to friction. We pushed human cognitive output to its absolute maximum theoretical limit.
Which brings us right to the precipice of where we are today. We optimized the writer, we made the person generating the code incredibly fast, but the source material argues that in doing so, we have slammed into the ultimate immovable wall.
The final wall.
We hit the final constraint. And it isn't about writing anymore.
No, it is not. The new bottleneck is the sheer speed of human review. The industry has spent decades figuring out how to help developers write code faster. But the traditional workflow still mandates that another human being must read, comprehend, and approve that code before it goes into production.
Someone still has to look at it.
Every single pull request, every line of code submitted to the main branch acts as a toll booth.
A toll booth. That analogy from the source really stuck with me. You can build a multi-lane, high-speed Autobahn for your developers. You can give them the fastest sports cars, the best frameworks, the most optimized laptops, and even early AI autocomplete tools.
They can drive down that highway at 200 miles an hour.
Right. But if they eventually have to slam on the brakes, pull up to a toll booth, and wait for a human operator in a little booth to manually review their ticket, verify the vehicle, and physically raise the gate. Well, the speed of the sports car is entirely irrelevant.
It doesn't matter how fast you got there.
Exactly. The throughput of the entire highway system is strictly limited by the speed of the human in the toll booth. The traffic jam just builds up. And for the professional listening to this, the real-world implication is stark. It means the foundational workflow we all use, where human review is the ultimate gatekeeper for quality and security, is fundamentally breaking down under the volume of modern software creation.
The math simply does not work anymore. The cognitive bandwidth of the human reviewer is the new bottleneck. And history tells us that when a bottleneck becomes this severe, the industry does not simply try to train humans to read faster.
You can't.
You cannot optimize your way out of a biological constraint. Instead, the industry innovates to bypass the bottleneck entirely. It demolishes the toll booth. Which brings us to the core subject of our deep dive, the arrival of write-only code and the inevitable death of the traditional pull request.
Okay, let's unpack this term carefully. Write-only code. Because I want to push back on this just a little bit. When I first read that phrase in the source material, my mind instantly went to the absolute worst legacy code bases I have ever seen.
The spaghetti code.
Yes. We all know what it's like to inherit a project where some developer, years ago, wrote this incredibly convoluted, undocumented spaghetti code that is so fragile and impossible to understand that the current team just refuses to touch it.
They treat it like a cursed artifact.
Exactly. It just sits there running in a dark corner and nobody ever reads it because they are terrified of it. Is that what we were talking about here? Are we just moving toward a world of automated spaghetti code?
That is a very common misconception, and it is vital that we clarify exactly what this term means in this new context. The source is very specific about what write-only code is not. It is not sloppy, poorly factored code that humans actively avoid reading because it is painful or technically indecipherable.
Okay.
We are not talking about technical debt generated by negligent human engineers. We must define what it is. In this context, write-only code is code generated at such a massive scale, with such high velocity and often such dense architectural complexity, that human review becomes structurally impossible.
Not undesirable, but impossible.
Precisely. The code itself might be syntactically flawless, it might be mathematically proven to be efficient, it might be structured perfectly according to the design patterns dictated by the system, but the sheer relentless volume of it dictates that it will never meet a human eye.
Wow.
It is conceptualized by a human, but it is written by a machine, deployed by a machine, and executed by a machine. The phrase write-only simply means that the human reading phase has been intentionally and systematically removed from the software development lifecycle.
So it's not that we can't read it because it's bad, it's that we literally don't have the time or the biological bandwidth to read it because there is simply too much of it being generated perfectly. And this explosion in volume is directly tied to the evolution of AI.
It is the direct result.
Now, anyone listening to this has been tracking AI coding tools. They've been around for a while.
Right.
But the source highlights a major inflection point happening right now. It draws a very hard line between the AI of yesterday and the AI of tomorrow.
Yes. The source clearly delineates the shift from AI as a copilot to AI as an autonomous agent. And the distinction is profound. For the last few years, the dominant paradigm has been the copilot model. Think of it as a highly advanced autocomplete.
Right.
The AI sits inside the developer's environment, and as the human types, the AI suggests the next few lines, or maybe it generates a boilerplate function based on a comment. It made human coders faster, undoubtedly. It smoothed out the friction of remembering syntax.
But the human is still in charge.
Crucially, yes. In the copilot model, the human is still flying the plane. The human engineer is breaking down the high-level business problem, designing the software architecture, managing the context, prompting the AI line by line, and most importantly, acting as the final toll booth operator, reviewing every suggestion before accepting it.
The human is still the editor-in-chief, but the source says that era is already ending. The new reality is the era of autonomous AI agents. And these agents operate on a completely different level of abstraction. They aren't just finishing your sentences.
Not at all.
If I'm understanding the source correctly, you can hand an autonomous agent a high-level goal, like, hey, migrate this legacy user database to a new schema, ensure zero downtime, and write the necessary API translation layers, and the agent just handles the rest.
Exactly. The capabilities of these autonomous agents are what break the toll booth model. An agent doesn't just write a single function. It takes that high-level goal, independently breaks it down into a sequence of actionable steps, plans the architecture, and begins writing the code across multiple files and services simultaneously.
It does the planning too.
And this is the critical part. These agents operate in a closed, self-correcting loop. They write the code, they automatically spin up a test environment, they execute the code, they read the error logs when it inevitably fails, they analyze their own mistakes, they rewrite the code to fix the bug, and they run it again.
They debug themselves.
They do this iteratively, thousands of times a minute, without ever asking a human for input or permission.
They are acting like an entire engineering team, but operating at machine speed. And that brings us to the productivity impact, which the source describes with a math-free reality check that is just staggering.
The numbers are undeniable.
It points out that as these agents scale, they're going to churn out software at a volume that makes human review mathematically absurd. Even if you hired every single human being on Earth, taught them all to read Python and Rust, and had them review code 24/7, the machines are going to generate functional, complex logic exponentially faster than human eyes can scan a monitor.
This raises an important question, perhaps the most critical strategic question for any technology leader or executive today. What do you do when your AI infrastructure can generate and test a million lines of highly functional, business-critical code in a single afternoon, but your senior engineering team can realistically only review and comprehend 1,000 lines a day? How do you resolve that mathematical discrepancy?
Well, historically, the answer would be you force the machine to wait. You maintain the toll booth because safety is paramount. You throttle the AI output to match the speed of the human reviewer.
But the source argues compellingly that the economic reality of the market will make that approach suicidal for any business.
Suicidal.
Are you genuinely going to throttle a 99% increase in software delivery speed just to maintain the comforting illusion of human control via a pull request? Are you going to tell your product team that a feature that could be deployed by an agent today has to wait 3 weeks for a human to read it?
They would riot.
Your competitor certainly won't wait. The competitive advantage of deploying custom software, tailored infrastructure, and complex digital services at the speed of thought will force companies to abandon the human review process. The economic forcing function is absolute. The toll booth will not just be bypassed, it will be demolished.
The toll booth will be demolished. That is an incredibly aggressive image, but it makes total sense when you look at the incentives. If a competitor can iterate their product 1,000 times faster than you because they trust their agents, and you are still forcing humans to read every commit, you're going to be out of business in a year.
It's an extinction-level event for slow companies.
But this brings up a massive, glaring issue. Here's where it gets really interesting. If you are an engineer listening to this, or a manager of engineers, your heart rate might be climbing a bit right now. If the AI is writing the code autonomously, and the AI is testing the code autonomously, and the business has decided that human review is a bottleneck that must be destroyed, what exactly is the human engineer going to do on a Tuesday morning? Does the software engineering profession just evaporate?
That is the natural fear. But the source material vehemently argues against that conclusion. The profession does not evaporate. It undergoes a radical transformation. It experiences what the text describes as an identity crisis and a rebirth all at once.
Okay, an identity crisis.
We are talking about a monumental role shift. This is the productivity bottom line for the average technology professional. Your value is no longer tied to the direct manipulation of syntax. The role evolves from being a hands-on author of code to being a high-level systems architect and, primarily, a constraint writer.
A constraint writer. I love that term. So if I'm understanding this, you aren't writing the step-by-step instructions on how to drive the car anymore. You are designing the highway system, and more importantly, you are building the concrete guardrails that ensure the autonomous cars don't fly off a cliff.
That is a perfect way to visualize it.
Let's dig deeply into this, because the source outlines 5 highly specific tasks that define the daily life of this new kind of systems designer. Let's break them down. Task number 1. The source says the engineer will focus on shaping the intent of the software, not the implementation. What does that actually look like in practice?
Shaping intent means focusing entirely on the pure business logic and the user requirement, stripped of any technical implementation details. Historically, an engineer had to deeply understand the business problem and then spend 90% of their time translating that problem into the esoteric logic of a specific programming language.
Writing the loops, the variables.
Exactly. In the write-only code era, that translation layer is handled by the agent. The human engineer's job is to rigorously define the what and the why, completely ignoring the how. You are no longer writing a JRA ticket that says, implement a Redis cache with a time to live of 60 seconds to reduce database load.
Which is how we do it now.
Yes, but now you are defining an intent for the agent. This specific data retrieval path must reliably return results to the user in under 50 milliseconds under peak load, regardless of the underlying infrastructure required. You're creating highly formalized, testable specifications of business value. The agent then experiments with caching, database indexing, or entirely new data structures to fulfill that intent.
You are setting the destination, and the AI is calculating the route. Okay, that makes sense. Moving to task number 2. The source notes that this new engineer will obsess over stable interfaces. Now, APIs and interfaces have always been important, but why do they become the absolute obsession in a world of write-only code?
Because when you have AI agents autonomously generating vast, complex webs of code that you will never read, the individual components of your system become total black boxes.
Right, you can't see inside.
You have no idea how the data is being manipulated inside those boxes. Therefore, the only way to ensure the entire system doesn't collapse into chaos is to rigorously control how those black boxes communicate with each other. The human systems designer becomes a diplomat or a treaty writer.
A treaty writer.
They focus entirely on the boundaries. If the billing microservice needs to tell to the user authentication microservice, the human engineer defines a mathematically rigid API contract between them. As long as the inputs and outputs of that contract remain perfectly stable and predictable, the human does not care what labyrinth of write-only code the agent has generated inside the billing service to make the math work. The interface is the only reality the human manages.
It's like managing a team of brilliant but entirely opaque subcontractors. You don't look at their internal accounting. You just make sure they deliver the right widget to the loading dock on time.
Exactly.
Okay, task number 3. And this is where it starts to get really intense. The source says the systems designer must define invariants. It describes these as the core rules of the system that can never, ever be broken. Can you give us a concrete example of an invariant in a high-stakes environment?
Certainly. The concept of an invariant is borrowed from mathematics and formal logic, but it becomes the bedrock of software engineering in this new era. An invariant is an absolute, non-negotiable law of physics for your specific software domain. It must hold true regardless of what state the system is in.
Okay.
Let's take a complex fintech application as an example. An autonomous agent might be tasked with completely rewriting the transaction routing engine to increase speed. It'll generate thousands of lines of write-only code to do this.
And no human reads it.
Right. Instead, the human defines a strict mathematical invariant. Under no circumstances, regardless of race conditions, network partitions, or logic errors, can a single transaction result in the creation or destruction of monetary value. The sum of the sender's account and the receiver's account must remain identical before and after the operation.
The math has to balance perfectly.
The human writes this rule in a way that the system can automatically and continuously verify against the AI's output. If the agent's code ever violates this invariant, even in a simulated test edge case, the code is immediately rejected. You are writing the laws that the AI is physically unable to violate.
That is fascinating. You aren't checking the math. You are building a box that makes incorrect math impossible to deploy, which flows perfectly into task number 4, defining failure modes. The source points out that a great systems designer doesn't just design for the happy path where everything works.
Because it won't always work.
Right. They have to exhaustively map out what happens when things inevitably go wrong. Because if we are trusting AI agents, we have to assume they will sometimes hallucinate or optimize for the wrong variable or get hit by an external outage.
Precisely. Designing a failure mode means predetermining the exact degradation path of the system. If a write-only microservice begins behaving erratically or throwing unpredictable errors, how does the system react? Does it cascade and take down the entire platform, or does it isolate the failing component?
You need a safety net.
The human must preemptively design the safety nets. You define rules like, if the recommendation engine fails to return a response within 200 milliseconds, instantly sever its connection to the database and serve the user a static, hard-coded list of popular items. You are architecting the graceful degradation of the system, ensuring that a localized failure generated by rogue AI code never becomes a global catastrophe.
And finally, task number 5. The text says the engineer is the one who decides which tiny, tiny fraction of the code still requires a human eye. Because despite everything we've said about demolishing the toll booth, there are still going to be specific, highly sensitive areas where you just cannot rely purely on automated invariants.
Yes, resource allocation of human attention becomes a primary engineering skill. Even in a hyper-automated future, there will be microscopic slivers of logic, perhaps a highly classified cryptographic key exchange protocol, or a core safety mechanism in a medical device,
Yeah.
or the final compliance layer for regulatory reporting where the business or legal risk demands human verification.
High-stakes stuff.
The systems designer looks at the entire massive architecture and says, the agent can write the UI, the database layer, the network routing, and the analytics tracking completely unread.
Yeah.
But this one specific 50-line file that handles the encryption protocol, we are putting a toll booth right there.
Just one.
The human decides where to spend their extraordinarily limited cognitive bandwidth for maximum risk reduction.
It's strategic bottlenecking. You only install a toll booth at the entrance to the nuclear reactor, not on every local street corner. And thinking about all of these 5 tasks, it brings us to a really specific and incredibly vital concept mentioned in the source material. It introduces a term called the slop radius.
Ah, the slop radius.
Slop radius. I want to spend some real time on this because it feels like the key to this whole paradigm. The text defines it as how far things are allowed to go wrong. It's the containment zone for AI errors. How does a systems designer actually manage a slop radius?
The concept of the slop radius is the absolute foundation of the security impact in a write-only code environment. Let's be intellectually honest here. If we accept that AI agents are going to rapidly generate millions of lines of code that we cannot read, we must mathematically accept that they will occasionally produce code that is flawed, wildly inefficient, or completely incorrect.
Inevitable.
In industry parlance, they will produce slop. Managing the slop radius means engineering the environment so that not if, but when the AI produces this slop, the damage is strictly quarantined.
I'm imagining it like designing bulkheads in a submarine. You know you are going into a hostile environment. You know a breach is possible. So you design the submarine with distinct sealed compartments.
Right.
If one compartment takes a hit and starts flooding because of a bad AI-generated update, the slop radius is the size of that one compartment. You lose that section, but the bulkheads hold and the flooding doesn't sink the entire submarine.
That is an excellent analogy. In software, managing the slop radius involves utilizing strict architectural boundaries. It means utilizing isolated microservices, rigid network policies, tight identity and access management controls, and database sharding.
Creating walls.
If you unleash an autonomous agent to optimize your email marketing service, you put a hard boundary around it. You give it access to the marketing database, but you mathematically prevent it from ever communicating with the central user credential database.
So it can't leak passwords.
Exactly. If the agent hallucinates and writes a script that accidentally deletes every table it has access to, the flop radius is contained strictly to the marketing department. The core business remains online. The professional systems designer's entire day is spent architecting these bulkheads, proactively containing the inevitable errors of the machines they manage.
It's like building a sandbox for a toddler with a bulldozer. You can build whatever crazy structures you want in here. You can knock them down. You can make a huge mess. But I've built a reinforced concrete wall around the sandbox so you cannot drive the bulldozer into the living room.
A bulldozer in a sandbox, yes.
That is the slop radius. And when you look at all of these new responsibilities, defining intent, creating stable interfaces, writing strict mathematical invariants, mapping out degradation paths, and engineering the bulkheads of the slop radius, it highlights a massive, massive psychological shift for the people doing this work. The text explicitly calls this out as an identity crisis for the engineering profession. And I get it. For 50 years, the pride of the craftsman in software engineering was tied directly to the code itself.
It absolutely was. The culture of software engineering has always been deeply rooted in the craftsmanship of the microscopic implementation. Engineers take pride in writing elegant, perfectly factored, highly efficient lines of code. They pride themselves on mastering the esoteric syntax of C++ or Rust.
It's an art form to them.
The artifact of their labor was the pull request, a visible, tangible document proving their cleverness to their peers. But in the write-only code era, that psychological anchor is violently pulled up. The pride must shift away from the craftsmanship of the specific line of code, which is now generated by a faceless agent, and move entirely toward the elegance, resilience, and safety of the macroscopic system. It requires a complete rewiring of what a professional considers a job well done.
The source summarizes this shift with a quote that I think is just brilliant. It says, "The core statement of the professional changes from 'I write code' to the much broader, much more strategic 'I build software.'"
Such a vital distinction.
Think about the massive difference in perspective there. Writing code is a localized task. It is typing syntax. Building software is a holistic outcome. And if you were listening to this right now, whether you are an executive managing technical departments or you are a mid-level engineer worried about your career trajectory, you need to internalize that semantic shift today. Your market value is no longer tied to how fast you can type or how well you remember the API for a specific library. Your value is in the building, the designing, the vision, and your ability to manage risk.
Which naturally leads us to the most daunting and critical challenge presented in the source material. We have established that the human reading bottleneck will be bypassed for economic reasons. We have established that the human engineer's role will shift entirely to macroscopic systems design and managing the slop radius. But this raises an important question, the ultimate dilemma from the text that we have to confront head-on. If we are not reading the source code, how on earth do we actually trust it?
How do we trust it to run everything?
How do we trust it to run our financial markets, to operate our power grids, to route our emergency services, or to manage our healthcare records?
Yes. Because we aren't just talking about letting an AI generate HTML for a local bakery's website. If that breaks, who cares? The slop radius is tiny. But software runs the world. Software is infrastructure. If no human eye has verified the logic deep inside these systems, trust becomes the single biggest obstacle to adoption. Now, what's fascinating to me is how the source material addresses this. It doesn't take the naive approach of saying, well, the AI models are getting really smart, so we should just trust them.
That would be reckless.
It actually takes the complete opposite stance. It emphasizes that in an era of write-only code, the need for provable correctness and strict accountability actually becomes more critical, not less. The standards for trust don't get lowered. They have to go through the roof. But it argues we simply can't rely on the old tool, the human gaze, to establish that trust anymore.
Exactly. For half a century, the human gaze was our primary primitive tool for establishing trust in software. If an experienced senior engineer looked at a block of code and said, "This looks safe," we trusted it. But human intuition is statistically terrible at catching complex, emergent logic errors in highly distributed systems.
I miss things.
Since we are removing that human gaze due to the sheer volume of code, we must replace it with something mathematically superior. And the source introduces a fascinating and, frankly, counterintuitive new proposed metric for this era. It compares it to the traditional concept of test coverage.
Test coverage.
In the old days, engineering teams would boast about having 90% or 100% test coverage, meaning they had automated scripts checking almost all their manually written code. But the new metric proposed for the era of AI agents is called code reading coverage.
Okay, code reading coverage. Let's break this down, because when I read this part of the source, it completely broke my brain. So, code reading coverage is a metric that tracks the exact percentage of your production code base that has actually been seen, read, and verified by human eyes. Sounds straightforward. And logically, you would think, okay, we are deploying AI agents, we are a little nervous about safety, so we should probably mandate a high code reading coverage. We should aim for 80% or 90% human review to be safe.
That's the intuition.
But the source takes a massive left turn here. It states that the goal is not 100%. The goal for the most advanced, secure engineering cultures in the world will be to drive their code reading coverage down as close to zero as physically possible.
As close to zero.
Wait, I have to push back hard here. You are telling me the ultimate goal of a world-class engineering team is for humans to look at 0% of the code running their business. That sounds like a recipe for a catastrophic, company-ending data breach. How can any sane CTO approve a 0% reading metric?
What's fascinating here is how this concept completely upends our traditional, deeply ingrained understanding of risk management. I understand why it sounds insane at first glance. For decades, human review was the gold standard of safety. But in this new paradigm of complex, autonomous systems, having a human actually read the code becomes a bad sign.
A bad sign.
It becomes a symptom of a systemic failure in your architecture. Think about it logically. If a human engineer is forced to manually read a block of generated code to ensure it is safe, it means your automated systems for building trust, your mathematical invariants, your failure mode definitions, your API contracts, and your slop radius containments are fundamentally inadequate.
They failed.
It indicates a total lack of faith in your own architectural constraints. It flips our idea of safety completely on its head. In this new world, human intervention is no longer the safeguard. Human intervention is the bottleneck, the primary source of friction, and statistically speaking, the most likely source of catastrophic error.
Wow. Okay, I think I see. It's like managing an ultra-modern, fully autonomous car factory. If a human worker has to walk out onto the active, high-speed robotic assembly line, stop the machines, and manually screw in a specific bolt on a chassis to make sure it's tight, that is not a sign of a good factory.
No, it's an alarm.
The human on the floor is a massive warning siren. It means the robotic torque sensors have failed. It means the automated quality assurance cameras are broken. The goal of the factory manager isn't to have humans checking 100% of the bolts. The goal is to build a verification system so perfect that a human never has to step on the factory floor at all. The human is a symptom of failure.
A symptom of failure, yes.
So if the goal is truly zero code reading coverage, how do we actually achieve that without flying blind? What is the security bottom line here? The source methodically outlines 3 foundational pillars of trust that are absolutely required to ship unread code safely. We need to go through these meticulously because these 3 pillars are the literal blueprint for the future of IT security.
Yes, these 3 pillars replace the human gaze. They are how you build trust in the machine. The first pillar is accountability. And this is crucial because it directly addresses the fear of algorithms running wild with no oversight. The source explicitly states that despite the autonomy of the AI, a human being is still firmly, legally, and professionally on the hook for the outcome.
We can't blame the AI.
We are removing the human from the tactical reading of the syntax, but we are absolutely not removing the human from the ultimate responsibility of the system's behavior. If an autonomous AI agent generates a massive suite of write-only code that inadvertently causes a severe data breach, leaks customer records, or triggers a flash crash in a financial market, the AI does not get fired.
The AI doesn't go to court.
The AI does not go to prison.
Yeah.
The human systems designer, the person who is responsible for defining the invariants, anticipating the failure modes, and containing the slough radius, is the one held completely accountable. The buck still stops with the human.
That is an incredibly heavy burden to bear. Think about the gravity of that. You are not reading the code. You have no idea what loops, conditionals, or data structures the AI used. But if it breaks the law or tanks the company, it is your fault, which makes the second pillar absolutely non-negotiable for anyone taking on this role. You cannot accept that level of accountability without the second pillar, which is control.
Precisely. Accountability without control is merely a scapegoat mechanism. If you are accountable for the macroeconomic outcome of the system, you must have absolute tyrannical control over the environment in which that system operates. And the source points right back to that critical concept we discussed earlier, the slop radius. Control in the era of write-only code is not about controlling the AI's keystrokes or dictating its internal logic. It is about controlling the arena. It is ensuring that your architectural bulkheads are so strong that even if the AI writes the most malicious, incompetent, or wildly unpredictable code imaginable, the physical structure of the system mathematically prevents that code from causing catastrophic harm outside its designated containment zone. You do not control the weapon. You control the blast zone.
You control the blast zone, and that takes incredible architectural discipline. Which brings us to the third and final pillar, tooling. Because you can sit in a whiteboard session and draw out all the invariants and slop radii you want, but you cannot enforce accountability or maintain that level of control over millions of lines of machine-generated code using standard human tools.
Impossible.
You can't just run a basic unit test and call it a day.
No, you cannot. Tooling is the ultimate differentiator. It is the bridge between theory and reality. It is what turns the act of shipping completely unread code from a reckless, dangerous gamble into a massive, defensible competitive advantage. We are not talking about standard linting tools or basic continuous integration pipelines here.
You need entirely new systems.
The source implies the necessity of world-class, mathematically rigorous automation. We're talking about automated proving engines. We are talking about formal verification systems, tools that don't just run probabilistic tests to see if a bug appears, but tools that use advanced mathematics to conclusively prove that the state machine can never enter an invalid state.
Mathematical proof.
We are talking about continuous constraint checkers that run at the speed of light, constantly monitoring the agent's output to ensure it adheres flawlessly to the human's defined intent. Without this elite tier of tooling, attempting to use write-only code is a guaranteed disaster. But with it, it becomes an organizational superpower.
So what does this all mean? When we take a massive step back from all the dense technical concepts we've covered today, the toll booths, the API contracts, the invariants, the slop radius, the formal verification, and we just look at the big picture of what it means to be a technology professional in this new era. The source reveals a really profound and actually quite comforting underlying truth.
I think it does.
It argues that the fundamental job of a software engineer was never really about just typing on a keyboard. It was never truly about memorizing the exact syntax for a dictionary in Python or a struct in C++R or arguing over formatting rules in a pull request. Those were just the tactical realities of the era. The true, enduring core of the profession has always been about reducing risk in a world full of ambiguity and constraints. It has always been about taking a chaotic business problem and solving a complex logic puzzle to deliver robust value to a user.
That is the philosophical and economic core of this entire paradigm shift. The medium is changing. We are moving from manual text entry to automated high-velocity generation. But the fundamental objective, risk reduction, logic structuring, and value creation remains exactly the same.
It doesn't go away.
That core responsibility doesn't evaporate just because an agent is writing the syntax. In fact, as the source persuasively argues, the responsibility gets exponentially bigger. It becomes vastly more strategic. Because the stakes are higher, the speed is faster, and the scale of the systems you're responsible for is orders of magnitude larger than anything a human could build manually.
The source uses a brilliant metaphor to close out this concept, and I think it perfectly encapsulates the career trajectory for anyone listening. It says the engineer is essentially being promoted from the engine room to the bridge of the ship.
The bridge of the ship.
Think about the history of naval engineering. You used to have engineers down below deck shoveling coal into the furnace, turning massive brass valves by hand covered in grease, manually monitoring the pressure gauges just to keep the engine running line by line, rotation by rotation. It was exhausting tactical work. Now, in the era of autonomous software, you are being called up to the bridge. You are looking out at the horizon. You are setting the strategic course. You are watching the radar for icebergs. You are defining the parameters of the journey. The AI agents are the engine room now. The engine room runs itself infinitely faster and more efficiently than you ever could. You are the captain.
And adapting to that transition, stepping out of the engine room and learning to command from the bridge, is the definitive career arc for the next decade of technology professionals. It is not an option. It is an economic imperative. Organizations that insist on keeping their engineers in the engine room, manually reviewing every rotation of the gears via human pull requests, will simply be outmaneuvered by organizations that trust their captains to navigate at machine speed.
They will be left behind.
Which brings us to the necessity of summarizing exactly what our listeners need to take away from this extensive analysis. As required by the focus of our deep dive today, we must rapidly synthesize the three crucial bottom lines regarding the historical, productivity, and security impacts of this shift.
Absolutely. We have covered an immense amount of ground today, but if you only remember 3 concrete things from this entire deep dive to take back to your team, make it these. Takeaway number 1, the bottleneck shift. We have traced the historical cycle of software economics from physical pet servers to scalable cloud cattle. The current reality is that AI agents are eliminating the human writing bottleneck.
Completely eliminating it.
Because of that sudden, massive increase in writing speed, human review is now the ultimate constraint slowing down the entire industry. History definitively proves that bottlenecks always get bypassed. Therefore, the traditional human pull request must be bypassed through the adoption of write-only code. The era of the human as the syntax gatekeeper is ending.
Takeaway number 2, the productivity impact. Because human review is mathematically impossible at the speed of AI generation, your role as a professional fundamentally shifts. You are evolving from authoring code line by line to high-level macroscopic systems design.
The bridge of the ship.
Your daily focus will radically change. You will spend your time on constraint writing, translating business intent, defining mathematical invariant rules, obsessing over stable API interfaces, and rigorously managing the slop radius to quarantine the inevitable errors made by machines. Your professional output is no longer measured in lines of code, but in the architectural resilience and safety of the system itself.
And takeaway number 3, the security impact. Trusting this massive volume of unread, machine-generated code requires completely flipping our metrics for safety. You must systematically drive your code reading coverage to near zero. A human reading the code becomes a glaring sign of systemic failure in your automation.
An alarm bell.
Instead of relying on the human gaze, you will rely entirely on 3 new pillars of trust. strict human accountability for the final outcome, rigorous architectural control to limit the blast radius of any failure, and world-class automated tooling to mathematically verify the AI's work against your constraints at the speed of light.
As we conclude this deep dive, I want to leave you with a final thought to ponder, one that builds directly on the deepest implications of the source material. We have firmly established the first pillar of trust, that humans are still strictly, legally accountable for the outcome of the system.
The buck stops with us.
Yet, as the text states, the software generated by these agents will operate at a scale, a complexity, and a velocity that is way beyond human comprehension. This creates a profound, perhaps even dangerous paradox. If a massive catastrophic failure occurs, perhaps crashing a global financial market, disrupting a supply chain, or disabling critical medical infrastructure due to an emergent microscopic AI decision that was literally impossible for the human brain to comprehend, simulate, or predict in real time, how will our corporate culture, and more importantly, our global legal systems, actually enforce that human accountability?
That is a terrifying thought.
Can a court of law truly hold a human systems designer legally and criminally culpable for the microscopic emergent behavior of an autonomous system they were physically, biologically incapable of reading? This severe tension between infinite machine scale and finite human liability is not a technical problem. It is the great unresolved societal question of the write-only code era.
That is an incredibly heavy and absolutely vital question to think about as you go back to your day, your strategic planning meetings, and your own software projects. The technology to generate unread code is already here. It is scaling right now, but the rules of our society, our courts, and our corporate structures have not even begun to catch up to the reality of what that means.
We are in uncharted waters.
And that is exactly why we are here doing these deep dives, to help you understand the bottom line and stay ahead of these massive, paradigm-altering shifts before they blindside your industry. Thank you so much for joining us on this deep dive. I want to aggressively remind you, if you found this breakdown valuable and you want to stay on the absolute cutting edge of these topics, you absolutely need to check out the Tech News TLDR YouTube channel. We post daily video updates matching the exact high-energy, fast-paced brand of analysis you heard today, breaking down the complex tech news you need to know without the fluff. Go subscribe, keep building the future, and we will see you next time.